So yeah, I'd like to introduce Dr. Brenna Argall. She's an associate professor of mechanical engineering, computer science, and physical medicine and rehabilitation at Northwestern University. Just gonna get yourself attached. I'll get out of your way a little bit. So she's the founder and director of the Assistive and Rehabilitation Robotics lab here at the Shirley Ryan AbilityLab. So Brenna's going to share her exciting work on partial autonomy powered wheelchairs and what the future holds for wheelchair users.
Thank you for the invitation to speak here today. So within the world of rehabilitation, of course, our first line of defense is to try to rehabilitate the body itself. But when a gap in function remains, we often fill that gap with functionally assistive machines. And there's a persistent challenge across this domain of how to control these machines, how to capture control signals from bodies with motor impairments in order to effectively control these machines. So this is perhaps most severely presented in the control of upper limb prostheses, where you have an array of EMGs that are trying to capture control signals to control a high-dimensional robotic arm and hand. But we even see this with powered wheelchairs. So a powered wheelchair is a two-dimensional control problem. You control speed and you control heading. And we can see here with different levels of spinal cord injury, for example, the interfaces that are available for people to use. So you start out with a joystick, maybe even a 3-axis joystick, which you wouldn't need for a wheelchair, but you could use for another type of assistive machine that needed more degrees of freedom. A 3-axis joystick also has twist. And as you go up, you're limited now to head arrays and then to sip and puffs. And what happens as these interfaces become more limited is that they're limited in a number of different ways. So one is the continuity or the proportionality of the control signal. So you go from issuing a continuous control signal, where when you deflect the joystick farther, you go faster, to a discrete, where it's just flipping a switch on and off, and you're always going the same speed. You also get limited in the dimensionality of the signal, where instead of issuing a two-dimensional control signal, you're issuing a one-dimensional control signal. And so now you can't fully cover the full control space at the same time, simultaneously. This is all the more exacerbated as the machine itself becomes more complex to control. So this is the Canova arm, or the Jaco robotic arm from Canova Robotics. It's designed to be mounted to a powered wheelchair, and it's sold with this 3-axis joystick. Just to position the end effector or the hand of a robotic arm is a 6-dimensional control problem. You need to define or specify position in 3D and orientation in 3D. So already this 3-axis joystick can't do everything at once, and you have to cycle between what are called control modes. So you push a button, you can control in position, push another button, you can control in orientation, push another button, you can control the gripper. So now, if you need to use one of these more limited interfaces, you are switching between even more control modes, and it just becomes all the more cumbersome. So here's an example of what this can look like. So this is actually a Miko robotic arm, which is the predecessor, the research predecessor to the Jaco, in my lab a number of years ago, being operated by someone with a high spinal cord injury. You can see that he is pushing the buttons with a utility cuff and a pen in the utility cuff, because he doesn't have the finger function to actually press the buttons. And that also you would have just seen, I think, just now. He actually did a mode switch, then tried to move the arm, saw that he was not in the control mode that he thought he was, and then had to mode switch again. And that's a very typical thing that needs to happen. And this is even using a two-dimensional continuous interface. So to sort of recap what I just discussed, there's a number of challenges to assistive machine operation. The ones that I just highlighted are the human impairment itself. And this impairment will actually mask and filter the information that the person would like to provide to the machine. Then there's the limitations of the control interface that are accessible to them. And this interface is limited in its dimensionality as well as its continuity. And then there's this catch-22 of machine complexity, where oftentimes the more complex motor impairments require more complex assistance, and that usually requires a higher dimensional control signal, which is all the more difficult to provide. So one solution that the research field has been addressing for quite some time is to turn these assistive machines into assistive robots. And what happens when you do that is that you need to add sensors that are able to perceive the external world, So what this can look like, for example, this is data that's being pulled from a Microsoft Kinect. So if any of you have ever used an Xbox, the sensor that is looking at you when you use the Xbox is the same sensor as we had on the early version of my wheelchair. What it's providing is a camera image, and then you see how it looks like it's flickering. That's because there's hundreds of thousands of depth points, so points that are coming back with a specific location in 3D space, and this gives depth information back to the system, which you can imagine is very useful for autonomous robot navigation, so you know what not to drive into. So you add on this external sensing, and then you reason about it with computing and artificial intelligence. You reason about both the information you're getting from the sensors, but also the information you're getting from the human. So in general, it is often the case that people don't want a 100% driverless car solution. They want to still be in the control loop. And so we're getting signals from them through whatever control interface it is that they use to drive their wheelchair, and we're reasoning about this, as well as the sensor information that we're getting, and trying to figure out what it is that we think they'd like to do, assessing that signal that we're getting for safety, and then figuring out if we should modify it in some way to get them where they want to go, but to do it in a safe way. And so then once you've done that, you have an assistive robot. So just to position this work within the larger space of rehabilitation robotics, so I tend to think of rehabilitation robotics in two big bins. One bin is robots that aim to rehabilitate the human body. So the Locomat would be a great example of this. These are robots that are moving human limbs or supporting humans in some way to rehabilitate their own body. The other big category are robots that replace lost function. These are the ones I talked about in the beginning of the talk. They're bridging this gap in function. And when we think about adding autonomy to these machines, there's a distinction that makes a big difference. And it's whether or not they're worn on the body, like a prosthesis or an exoskeleton, and whether or not they're not worn on the body, like a wheelchair. And the reason why is because you have to add those sensors and that computing, and it needs to go somewhere. So if it's all embedded inside of your prosthetic limb, and then it's all that additional weight, and you had to somehow get it inside, and it's just hanging off of the arm, that is a much harder engineering problem to solve from a human factors perspective than just throwing it on the wheelchair that's already carrying the person and pulling from the wheelchair's batteries. Okay, so within this approach, the devil is really in the details when it comes to this computing and AI. Particularly, how are you going to share control with the human? So now you've got control information that's coming from your robotics autonomy system that can drive itself if it needs to, and from the human. And so how do you reason about how much to consider one versus the other, or when to prioritize one over the other? So when we consider that we should be developing assistive partial autonomy, there's a couple of things that my lab prioritizes. One is that the control sharing should be judicious. The reason why is because if the autonomy steps in at the wrong time or with the wrong signal, they're actually taking control away from the person. They're making them less able, which is exactly what we are not trying to achieve. So you can imagine, perhaps in the exception of cases for extreme safety, that just not doing anything is actually the better thing to do, to not intervene. And then also the fact that the information that we're getting from the human is masked and it's filtered. Their true intent is masked and filtered both by their motor impairment as well as the interfaces that are accessible to them. All right, so I'm going to talk about this judicious control sharing first. So these are all control sharing paradigms that come from the robotic wheelchair literature. So these are academic researchers involved in what are called smart wheelchair research. These have all been published. And the way that they differ from each other is that the way that this is color-coded is that the signal you're getting from the human is in red. The signal that you're getting from the autonomy, so this is the robotics autonomy, is in blue, and then the signal that you're actually choosing to execute is in purple. And there's a couple of different things. So one thing is that the human is actually, or the autonomy system is actually trying to infer the human's intent from the control signals that they're getting. So you can see at the top, we have a paradigm for what we call immediate goal inference, where we basically just take the human's control signal, we forward project it a half second in the future. So we're saying, I don't think I know that much about what you're trying to do. I'm just guessing if you said go forward, in a half second you'd like to be there. That's all the inference we're making. And then we get a temporary sub-goal to send to our robotics planner that can plan a safe path to it. We also have higher level algorithms that you see on the bottom here, for example, that can detect a doorway. And so you can detect that this is a feature of the environment that often is difficult to navigate. And so we're going to say that that is actually our navigation goal, if we're getting the right signals from the human, that it seems like that's where they want to go. And you can see that depending on what goal we choose, the planner is going to do different things. And depending on how we're then arbitrating between the human and the planner and the autonomy planners signals, the actual purple arrow that we're going to get out of it changes as well. So we might blend the two. So you just sort of find something in the middle that's safe but as close as possible to the human's control signal. It might be that we filter it. So we basically say the human signal just can't exceed the autonomy signal. We're going to keep the human signal, except we're going to scale it down so that it's safe. Because we're presuming that the autonomy signal is safe because it has this sensor information from the environment. Or we can do something that's a little bit more aggressive, like switching, where we basically say, we're going to get you close. With your control signals, we'll get you close to the door. And then to actually get the door, we're just going to take over the control 100% just for navigating through the doorway, because that's a tough thing to do. And then we'll give control back once we're on the other side of the door. So we implemented all of these on my robotic wheelchair. This is not something we had seen in the literature before. We had seen lots of comparisons of partial autonomy to full autonomy, or full or partial autonomy to no autonomy. But a side-by-side comparison of these different ways to share control we had not seen before. So we implemented all of them, and what you might notice is that they don't look that different from each other. And this is what we saw in the data too. According to the measures that we normally use to evaluate robotics autonomy, like number of collisions, task completion time, none of them were statistically different from each other. What we did see, however, was a difference in preference. So we asked everyone to rate their most preferred and their least preferred, and we allowed for as many ties as they wanted. And what you can see is that while we do have a general trend of some being more preferred in general, every single paradigm was actually chosen at least once by someone as their most preferred paradigm. What we also saw, and we did have some work also where we tried to predict that preference using just computable data from the wheelchair. What we also saw is that about 50% of the time people switched their preference when they switched the interface that they were using. So all of the participants in this study came in one session day, they used the joystick, and in a second session day, they used the head array, and we switched which one came first. You see here that there's 2 to 4 sessions. That's actually because the sitting tolerance of some of our spinal cord injured participants meant we had to split some of the sessions in 2. But it meant that the interfaces themselves happened on different days. And so what we don't really know is whether or not this switch in preference had to do with the interface itself, or if it's just an overtime, if it was familiarity with the autonomy. But our big takeaways from this study were basically that we should be giving people options, and we should expect that those options will change over time, or that people's preference over those options will change over time. So I'm going to add to my list here that one thing that's missing within the literature of this work are longitudinal and real-world evaluations. So typically when people come into academic labs and evaluate one of these shared control paradigms with robotic arms or robotic wheelchairs, they come in for 1 session, maybe 2 sessions. So we are always evaluating novel interactions with these technologies. And obviously, that is not what things are going to look like necessarily long term. We all change in how we interact with technology over time. You compound that with the fact that actually people's bodies are changing as they're undergoing rehabilitation. And so we know that things are going to be changing over time, and we have not studied that yet, we as a field, my lab included. So this study and a number of other studies my lab had done established for us the need for customization. So then the question is, how do you actually achieve it? How do you achieve it so that this system can change on its own and do it in a way that is not going to throw the person off because it's changing and now they can't anticipate what it's doing, but is still changing enough to meet their needs? To start answering this question, we performed in my lab a large-scale usage characterization study. So what this looked like was that we had 62 sessions. We had 20 spinal cord injured participants and 42 uninjured participants, and we had them operate 3 interfaces. The uninjured participants operated all 3 interfaces. The injured participants operated the interfaces that they could. So we had a head array, we had a joystick, and we had a sip and puff. And we also had 7 tasks. So and for those of you who are going on the tours later today, you'll see this obstacle course that we have, this wheelchair obstacle course that we have up on floor 19. This is where my lab evaluates our robotic wheelchair. It consists of a number of characteristics or environmental features that can be difficult to navigate in a powered wheelchair. So this is where we do a lot of testing, and actually inpatients use this as well. They do use this a lot for therapy. And then we did, at the start of each session, we gathered 3 baselines. One was a clinical standard that some of you maybe are familiar with, the wheelchair skills test, and 2 of them were tasks that we developed on our own. And these were virtual tasks. One was a command following task where we would just present a target prompt as an arrow, and we would ask people to reproduce it with their interface. And then the second was a trajectory following task where we basically had an outline, a very crude outline of a 2D wheelchair, and a direction prompt that said, go this way, and then you're trying to stay on that white path, or you might have a direction prompt that's telling you to go backwards. And what we were trying to do with these assessment tasks was try to decouple operation of the wheelchair itself, which can be complicated by the environment, by perception, and just see how well people can actually use the interface, operate the interface, and also do a little bit of path planning in their head and operate the interface. What we weren't expecting was how much we would get from this. So we first published our initial findings from just doing this first 5 minutes of data collection in each session in ICOR in 2019, and then we've actually continued to evolve this. We've turned this into an app that therapists can use. We have a beta release on the Android Play Store, and we're currently having therapists evaluate this in my lab. So it's available free to download. It is still very beta, but certainly send me an email if it's something that you might be interested for yourself or clinical teams that you work with. All right, so when we did this initial analysis, one thing that we saw was that between the interfaces, we did not see a significant difference in success. So whether or not you're using a joystick or you're using a sip and puff or a head array, everyone, the ability to eventually reproduce that arrow command prompt was similar across, not statistically different across all the interfaces. What we did see, however, was a difference in response time. And this has a number of different implications for robotics autonomy that I don't really have time to get into here. But one thing we looked at additionally was that all of our spinal cord injured participants were an expert in one interface because there are wheelchair drivers in their daily life. So we divided out their data into the interface that they were an expert at using and the other interfaces that they were not experts in. And what we saw was that this difference in response time started to normalize. So it also can improve with expertise. And so this, again, is telling us that people are going to be changing in how they're interacting with machines over time. So we thought we were onto something here. And this has actually initiated a whole new line of research in my lab that we're calling interface-aware assistive autonomy. And what we're doing is we are actually modeling the person, a specific person operating a specific interface, and we're reasoning about that. So we can now think about when we're going to provide robotics assistance, we can now think about if it seems like this isn't the signal you wanted to give the wheelchair, because, for example, it's about to run into a table, are there characteristics in how you tend to operate your interface that would suggest that actually maybe you meant this other signal that sometimes you issue instead of this, and we can then send that other signal to the machine. So that's the general flavor of this work. I don't have time to go into any more of this in detail. But it's an exciting new direction for my lab, and we don't know of anyone else within the assistive robotics field that is taking this view or this approach to providing assistance. Okay, I will actually skip over this in the interest of time. The final thing that I wanted to speak about today is that my lab is involved in an exciting initiative that's being offered through the National Science Foundation. It's their Convergence Accelerator Program, and this is aimed at specifically translating technology out of research and into the real world. I'm leading team H354, and what we are aiming to specifically address are barriers to independent mobility. There are 2 barriers that we're focusing on in particular. One is a dearth of control interfaces that are able to capture control signals from bodies with motor impairments wherever they have residual movement. So not requiring people to meet the form factor of the device, and instead having the device conform to the user and where they have motor ability. The second is a relative lack of assistance, safety assistance, but actually even just driving assistance options in powered wheelchairs. So we've all seen throughout the rest of society driverless car solutions, like robotics autonomy showing up all over the place, even just in our regular cars, right? Things like parking assist, lane assist, emergency braking, that kind of technology, there's no reason why that can't exist on powered wheelchairs. And so we are trying to get this technology out to market. We have a really great group of partners on this that include nonprofits and as well as industry. And I'm going to highlight in particular Lucy, which some of you may have heard of. Lucy is an aftermarket add-on to powered wheelchairs. It was the first and remains the only sensor-based safety system add-on for powered wheelchairs. They entered the market in 2020, and the kind of assistance they provide is what's called subtractive only. So they will stop you. They will, if you give a signal that's in this direction, and actually right there is going to be an obstacle, they'll maybe remove energy from your signal selectively so it looks like they're steering you, but they're actually never adding to your control signal. And of course, there's a lot of things that you can do if you actually have that active assistance. And so that's what we're doing in this project. We're adding MyLab's active autonomy assistance into the Lucy system. So right there you can see the new wheelchair in my lab. We got this chair about 15 months ago. It was donated to us by Sunrise to be able to do this work. Lucy donated to us a system, and we rebuilt my lab's robotic wheelchair on top of the Lucy system, which is far more stable in terms of the sensor information it provides, because it's not cobbled together with academic levels of rigor. And so that's a major thing that we're doing here. And the third component to our work is what's listed here as thrust 2, the digital input mechanism. So right now, many of you might be familiar that the way that the wheelchair interface communicates with the wheelchair control system is through a 9-pin DBN serial cable. It's a printer cable, right? It can't be brought into the digital world. It can't be updated. It cannot provide bidirectional communication. And what we're developing is a digital API. It's actually already released, but we're expanding its capabilities. A digital API that uses common human interface device, HID protocols, for how to communicate between the wheelchair and the wheelchair's control system and any input device. So what this is enabling, because it's digital, right now it works with Lucy, because Lucy provides USB and as well as Bluetooth capabilities on the wheelchair. So you can actually connect any interfaces that get used for gaming, which there are much more advanced interfaces for gaming, for example. You can use that now to control your powered wheelchair. And what we just submitted 2 weeks ago, our phase 2 funding. So this was phase 1 funding, which is pretty much just to prepare you for phase 2. It's a 12-month grant. We've got 2.5 months left on it. And then for phase 2 is when you have 2 years of funding to really accelerate and get this all out the door. So we've submitted our phase 2 funding. I think about a third of teams who have phase 1 funding will get phase 2 funding. But fingers crossed, if we are able to do if we get the funding and we're able to do what we promise in that grant, it should be that active assistance is getting rolled out with Lucy products within about 2 years from now. And that also this new interface that we're developing, we're hoping to have sort of pre-production prototypes. We won't yet be to market yet, but we will be sending it to people to evaluate. And our aim is that our communication protocol will actually become the standard for powered wheelchairs. So that's all. I'd like to thank my current PhD students and some alumni whose work was featured in this talk. And I don't think we're taking questions, so I'll be happy to take your questions later. Yeah, okay.